Hello, this is Information Service Engineering, lecture number 2, Natural Language Processing, part 2. In this part of the lecture, we are going to discuss language models and n-grams. And let us start by taking up the idea of word prediction. So what does word prediction mean? So it is the notion of where we want to predict a word that comes after a given sentence or a given sequence of existing words. For example, we have the following sentences here: to be or not to, or the pen is mightier than the, or you can't judge a book by, and some sentences in German for the German speakers. So we as human, we probably can tell what is the word that is most likely to follow the sentences or half sentences we have here. And we do it because we have some prior knowledge. And the knowledge that we have as human might be domain knowledge. For example, if we know the topic that we discuss or a topic of a text, we would be able to tell if the word that follows the word red would be blood, so if we would have red blood, or it would be the word hat, so red hat. Also, we have syntactic knowledge. So as human, we know that the word the in English is followed by an adjective or a noun. And then there is a lexical knowledge we have. So that's why we can distinguish between baked potato or steak. So the claim here is that there is a useful part of knowledge which is needed to allow for word prediction. And this specific part of knowledge can be captured using simple statistical techniques. And here it comes the n-gram models. So the word prediction can be formalized with probabilistic models, which are called n-gram models. So these models, they let us predict a word or compute the probability that a word follows a sentence, given by taking account the words of the sentence. And this n here can be a natural, is always a natural number. So it can be 2, so we can have a 2-gram or big-gram, where is a 2 token words element from a sequence of words, where those 2 words follow one the other. So from the sentence that we have to be or not to, the big-grams that we get are those sets that you see here. So to be or not to. Also, we can have a 3-gram or 3-gram, as it's called, where here we have a 3 token words element. So again, from the same sentence, the 3-grams now they look like to be or not to. So to generalize, an n-gram is an n token of words. And in an n-gram model, the last word, which is w sub n, depends only on the previous n-1 words. And this is known being called as Markov assumption. So based on this assumption, the last word of a sentence, so the w sub n, will be computed from the previous words n-1. So statistical models like the n-gram models of word sequences are called language models, or LM as we usually find it. And they are rather useful, so these n-gram models, especially in tasks where we have to predict some word which comes from a noisy or ambiguous input, which is often the case, for example, in speech recognition. So in speech recognition, n-grams are rather useful to help us correctly identify the sentences, since there are some words that they sound similar, almost the same. So using n-grams, we will correctly identify the sentence computers can recognize speech instead of computers can recognize speech. But it's not only speech recognition, so we can use n-grams for handwriting recognition, for spelling correction, machine translation, authorship identification, sentiment analysis, and many more tasks. But before going into how we can actually compute those n-grams, let us first have a look at some basic probability theory we would need here. So first, it comes the trial. So the trial is an experiment, as we can else call it, so for which we want to measure a probability. So it can be, for example, throwing a dice or predicting a word. Then it comes the sample space omega, where here is a set of all possible outcomes for a given trial. So given our examples, we can have all possible numbers coming by throwing a dice, or all words in a Shakespeare's play, or all numbers in a lottery. And then there is the event. So the event is an actual outcome, which is of course a subset of the sample space. So here an event would be throwing a 3 or throwing a 5 or predicting the word the. And then there are some very helpful axioms we need to know here, which are called Kolmogorov axioms. So there are 3 axioms proposed by Kolmogorov. So the first one says that each event has a probability, which is denoted by a capital P, between 0 and 1, formalized in this way. The second Kolmogorov axiom says that the null event has a probability equals to 0, while the probability that any event happens is equal to 1. And the last Kolmogorov axiom says that the probability of all disjoint events sums to 1, given by the formalization here. And let us continue with the conditional probability. It's a rather important probability here, which we are going to use often. So the conditional probability is a way to compute a probability of an event, given that another event has already happened. And here in the equation we say that the conditional probability of B given A, and this is how we read it, means that the event B occurs under the assumption that the event A has already occurred. And to compute it, we have to compute the probability where both events A and B happen and normalize or divide to the probability that the event A happens. And then we continue with the joint probability, which comes after rewriting based on the Bayes formula. So the joint probability of A and B is the probability that the event A occurs followed by an event B, this time here, and is equal to the probability that the event A happens, multiplied to the conditional probability that B happens given A, as we saw right before. So given that the event B occurs under the assumption that the event A has already occurred. And this joint probability can be extended to 4 events. And here we see that we want to compute the joint probability of the events A, B, C, D happening all together. So this is equal to the probability of the event A, multiplied to the conditional probability of the event B, given that A has already happened, multiplied to the conditional probability of the event C, given that both A and B have already happened, and last, the conditional probability of the event D, given that all events A, B, C have already happened. So this probability can be rewritten in this way, which is to conform into a sequence of words. And this is the generalization actually of the Bayes theorem for modeling a sequence of words in a natural language. And this is what we are going to use from now on. And let us just check a small example how this would apply in a sequence of words or in a small sentence, in the one that we already have. So to compute the probability of the sentence to be or not, first we have to compute the probability of the word to, multiplied to the conditional probability of the word be, given that to has already happened before be, multiplied to the conditional probability of or, given that both words to and be are already there before or, multiplied to the conditional probability of the word not, given that all 3 words to, be, or are there before the word not. So in the next part of the lecture, we are going to go deeper into n-grams and see how we actually compute it, and so we will continue with the second part of language model and n-grams.